Hey, this is OXDF, and I'm looking at another challenge today from the HackTheBoo CTF, Halloween-themed, beginner-focused. And today I'm going to look at a crypto challenge. The crypto challenge from the second day is called Fast Carmichael. It gives us both a Docker to spawn and a downloadable file. We'll start by taking a look at the Docker. So we'll go ahead and jump in here. We can netcat to that, and we just need to replace this colon with a space, and it says give p. And so if we put in like a number, because crypto sounds like it needs P, and it says conditions not satisfied, and it dies. So with that, let's go ahead and pop open. Oh, I already got VS Code open here on the single file. Let's see. The file has a single download, server.py. And if we open up VS Code, we can take a look. Start down at the bottom here. We can find if name is main, it's going to call these various things. It's going to create a TCP server handler. It's going to create the reusable TCP server handler on port 337. That's what's going to get passed through to my Docker, presumably, and it's going to serve forever. If we look up at the reusable TCP server here, it's doing nothing fancy. But if we look at the handle function, it's going to call main on self.request. So we can come down here to main. And main is going to receive message with the message give p. So that's probably what we saw in our Docker. And it's going to read, let's see, so S is the socket, and it's going to store that in p. It's going to try to convert that to an integer, otherwise it's going to fail. And then to print the flag, we need something that is going to pass is prime and not pass is prime. So the first is prime is this one right here. So if p is less than 1, return false. If not, Miller-Rabin 300 return false, otherwise return true. So it's this Miller-Rabin function, which is right here. So it's some test of trueness, of primeness. And we need that to return true, that it is prime. The other is prime is actually imported from the crypto util number library. So I'm going to make the assumption here that the one in the library is robust and is good, and is telling us whether it's actually prime or not. And that the one implemented here is missing something. It has edge conditions. So we could do some analysis of this Miller-Rabin function. But at this point, actually, we'll start going down doing some searches. So what is Miller-Rabin? And the Miller-Rabin primality test, that sounds pretty good. It's a primality test. We can read about this. It basically goes through and shows this, and if we look at what's in there, I think it matches pretty nicely what's going on here. So I don't get a ton out of this. The other thing to think about is that the title of this one's called Fast Carmichael. So if we search for Carmichael primes, we're gonna get this Wikipedia page on Carmichael numbers. And what's interesting about this is if we search for Miller-Rabin, we have a hit. So this basically says Carmichael numbers will pass a Fermat primality test to every base B relative to the number blah, blah, blah. This makes tests on Fermat's theorem less effective than strong probable prime tests such as these two here, including this one. However, no Carmichael number is... So again, is this something like gobbledygook to you? It kind of is to me too. But the point is that these Carmichael numbers are basically numbers that look prime to a lot of the modern tests we use to try to speed up prime checking. It's actually quite difficult to tell if a number's prime when it's 1,000 digits, right? Like, how do you know? So we have all these algorithms that do a best guess at whether they're prime, but these Carmichael numbers are numbers that prove them wrong or look prime to these algorithms but aren't really. And so there's this specific example of a Carmichael number here, which is this n number, which is defined by p, where p is this long number. And so it's going to sound kind of silly, but what happens if we give that number to our thing? So we can say, come over here. Oops, let's go back to our terminal here. And we'll leave that here, and we can open up Python down here. And we can say p equals, and paste that bad boy in. And now we need to say n. Let's see if we can make this fit on the screen together. Right there. So we can say capital N is equal to p times 3130 times p minus 1 plus 1 times 353 times p minus 1 plus 1. If I type all that right, we can print n right now, and it's a long number. Let's copy that and come up here and give that as p, and is hanging for a minute and gives us the flag. So that's it. Actually, this is rated as a very easy challenge, and it's not that easy in the sense that like the math is not trivial. I don't actually understand all the details of what's going on here, but I understand at a high level, and I can do some high level analysis to say prime numbers are hard to identify. Checking if a number is prime for huge numbers is not trivial. We have algorithms that try to do it in a fast way, but they're not perfect. And these Carmichael numbers are examples of numbers that look prime to these algorithms, but aren't really. And so we took this one right here, this 397 digit Carmichael number, and we gave it to our algorithm, or to the Docker, and we got the flag. So that's it. This is short and sweet. Hopefully you enjoyed the video. Thanks for sticking around, and I will talk to you next time. Bye.